time I essentially defined K groups of a exact category. Okay, and so let me just go through it quickly. So if E is an exact category, then we define a so-called Q category. Okay. So so they are like this. There is a surjective map from Z. So I'm defining. So objects are same. I'm defining a map from X to Y. So this is a pair of morphisms. One of them is surjective, or we call it deflation also. And deflation, epimorphism, admissible epimorphism. On left side, you have a injective map. You can call it inflation, and also admissible monomorphism. And so, so there is an equivalence relation. Okay, so these are the morphisms from X to Y. Okay, and so let me not go through the equivalence relation definition. This is how composition is done. And so I explained here what happens. So if you are working with projective models, so Z, this middle thing is Z. Projective models, all those admissible epimorphisms and monomorphisms they split. So this is my X and that's my Y. So this is how it looks like. Okay. So there is no natural functor from E to QE, but given an inflation, you can associate a map in the Q category by using identity. Okay. So identity, the extra map you need, you use identity. So then, and that's important. So I said that from classical K-theory, K0, Gaussian group, to pi 1 of this classifying space of this Q category, there is an isomorphism. And to do that, I'm using exactly what I just said. You have the map from 0 to X. Okay. That's the 0 map, of course. And you also have the map from X to X, that's the identity map. You use this to define two maps from 0 to X. So, and each arrow corresponds to a line, okay, or or a path. So you can combine them to define a loop at 0. So that is the association. Okay, so given an X, you associate that to this loop. Okay, and this is an isomorphism. Okay, and so I can define hierarchy groups Kn pi n plus 1 of the classifying space. Pi 0 is 0 because classifying space in this case is connected, because there is 0. From 0, you always have a map to any vertex. So anyway, that's my Kn. Okay, of course, K1 of projective models. Okay, for any category, of course, by this definition, there is a K1 and K2, but we are familiar. We knew a definition of K1, and that coincides. This needs a serious proof. Okay, I simplified the proof. I may make a few more comments on that. Okay, so K0, K1. You also have K2. Okay, so that also coincides. Okay, K2. So these are the three groups that we had 30 or 50 years ago. Okay. Now, one more point, important point, of course, that if you have a functor from one exact category to another, functor meaning not any functor, exact functor, it maps takes exact sequences to exact sequences. Then there is a natural map from it induces a natural map from this KNE to KND for all n. I mean, I wrote 3 lines. These are more or less equivalent statements. So, I mean, I think the second line is easier to see. Classifying space of Q of E to classifying space of Q of D, there is a natural map. Okay. And then I mean, and its homotopy groups are K groups, so we have the map. And third line is the loop space of the classifying space, which essentially, basically, it is K. It helps us to write Kn of E as pi n of Ke instead of pi n plus 1 of the classifying space BQE. Okay, so this is all natural, I mean, so given an exact category, you have a classifying space, and given a exact functor, we have a map of the K groups. Basically, I mean, I want to make this point that I mean, we algebraists, of course, like to talk about the groups Kn of E. And I would say that has been customary even in to an extent in K-theory also. But the map of the classifying space or the loop space has all the information. Okay. So first you define the classifying space, and unfortunately there is no good description of K1 or K2. Okay, even for predictive models, K4 and all, there is no good description. Okay, I mean, that's a part of that's the kind of work, I mean, commutative algebraists can do. I mean, unfortunately, even I'm saying even K1 is not well understood for I mean, far from being well understood. Even describing K1 of category of finitely generated module, that's a big deal. Okay, there is a definition, but it needs to be looked at more carefully. Good. Now I define. Okay. Now we know what are the theorems to expect. Okay, in K-theory, that's how it has been, I mean, what are the theorems you expect. Okay, so those theorems are proved. Okay, or I'll state them. Suppose we have 3 functors, G, F, and H from E to D, exact functors, of course. Okay, now suppose they these 3 functors form an exact sequence. So meaning for all objects, G of x 0 to G of x to f of x to h of x to 0 is an exact sequence for all x. Then the maps induced by the middle one, f star, is same as sum of map induced by other 2. Okay, G star plus H star. So, and what's an example? Okay, so you take a project P1 and P2, 2 projective modules, and P be the direct sum. Now, if you look at the category of finitely generated module, which I denote by COHR, there are 3 functors. Okay, these are exact functors. Okay, and they form an exact sequence of functors from COHR to COH, coherent models on R to coherent models on R. Okay, so so this 2 will induce yeah, all three induces map, and the middle one, this map induced by tensor product P is same as sum of the other two. Okay. So this actually, one good important thing to note here is that this induces a K0 action on Kn of Kh. K0 of R, meaning I'm talking about projective modules there. That's the projective modules, okay? So K0 of R to, so there's an action like this, okay? And I may be in trouble, my battery. Okay, fine. I'll see what I can do. So anyway, and these things work for schemes, okay, and locally free shifts. So you replace projective models by locally free shifts, okay, and okay, fine. So that is called additivity theorem, okay? And I gave you an example. So now you have, suppose I have an exact category, P be a full subcategory, okay? Okay. So basically, I'm thinking of category of coherent modules or finitely generate modules over a ring, and I'm thinking of projective modules. Okay, so and that is and that has certain properties, you know. I mean that if I give you an exact sequence in E, if K and C are in P, then M is also in P, and if M and C are in P, then the kernel is also in P. Okay, like projective module, and any module has a finite resolution by any object in E is has a finite resolution. I mean, this normally we wouldn't have unless my ring is regular. Okay, so these are sometimes called resolving category. I have never seen this anybody using in K-theory, but some commutative algebraists use this this thing. Okay, they call it resolving category. So anyway, so if you have that, then you know this Kns will agree. Classifying space will be homotopy equivalence, and the K-theory space, that is the loop space, okay, that map also will be an homotopy equivalence. And see, this is I said, you know, these three are essentially equivalence statements, okay. So yeah, fine. Now you see. So what's the good example? Example is, again, I'm thinking of projective models over a ring, but I'm not thinking of category of coherent modules. I am thinking of category of the subcategory of all modules which has finite projective dimension. Okay, so these two agree. And you know, I don't know, I mean, at least if you have done any K-theory, you know, K0 of these two things agree. We always knew that, okay. Basically, I would say Quillen just made that proof work, okay. So if you assume R is regular, then right hand side, HR is the category of coherent modules, okay. Yeah. Meaning finitely generated module. Okay, so again, this works. If X is a scheme and you replace PR by category of locally free sheaves. Okay, and yeah, one difference between projective modules of affine case and non-affine case is that in affine case, I know any module is the image of a projective module or free module actually. In non-affine case, that is not there. That has to be a hypothesis. Okay, I mean there are conditions, of course, ample bundles and such things. So in any case, right? What else you expect? So resolution theorem you expected. Okay, and I gave you that. And what is the other theorem you expect? That K-theory of R, a ring, should be same as K-theory of the corresponding reduced ring. We expect that. Actually, I will show you that doesn't always work, but at least for coherent. So anyway, so I stated a theorem. Suppose B is a full subcategory of A. A is an abelian category, not just exact category. Okay, so B is closed under sub-object, quotient object. Basically, I'm saying that B will be a abelian subcategory of A. Okay, now given anything in M, any object in M, it has a resolution by objects in, not resolution, filtration by objects in B. So that quotient is in B. Okay. So this you can see for modules, you can do this for, you just, for example, if you take the category of finite length modules, you can do this. Okay. So, yeah, local ring, you take a local ring and think of the category of finite length modules. You can resolve it by so quotient will be just isomorphic to K, meaning vector spaces over K, over the yeah. So anyway, so if we have that, if we have this kind of filtration, then K-theory agrees. Okay. So 3 lines I wrote, as I said, they are essentially equivalent. Okay. So yeah, middle line, second and third line will be homotopy equivalence. First line is isomorphism. And so, I mean, I told you the expected theorem. I mean, example, I have been talking about it. So R will be a commutative ring, then R reduced is, K-theory of coherent modules of the corresponding categories. Yeah, will work. Okay. Yeah, finitely generated modules, it will work. They will coincide. Okay. Yeah, I mean, and this is very interesting. Okay, that I cannot say K1 of a reduced, K1 meaning the projective module, K1 of projective modules, which we can compute, okay, is same as, yeah, these two don't agree, okay. I mean, K1 of, if you're working with local rings, K1 is the units in the ring. So you can easily cook up examples. So I wrote this works for schemes, but I mean the previous line, this K-theory of will agree. And it has a lot of applications, okay? Okay. So, what else do you expect? You expect long exact sequence, so-called localization sequence. In affine case, it never worked too well because there is not very many, open subset of spec A is not affine anymore. Okay, so that's why there's not enough of those things. But anyway, I'll come to that. So suppose we define say subcategory of an abelian category, not exact category. Okay, so what is that? If you have an exact sequence in A, and if K and C are in B, then M is also in B. I mean, this is a if and only. Okay, main point of say subcategory is that quotient exists. Quotient of A mod B, okay, exists. Okay, and so I can state a localization theorem. I mean, quotient goes with localization. Okay, what you call in commutative algebra we teach localization. That is a quotient category. Okay, and so if you have say subcategory of an abelian category, then the map, this sequence of functors B to A, that's the inclusion to the quotient, okay, is a homotopy fibration. I mean, by that I mean the classifying spaces, okay, map, the sequence of classifying spaces is a homotopy fibration, okay, which means you may have forgotten, some of you may have forgotten definition of homotopy fibration I gave, but it means you can write down a long exact sequence of the homotopy groups, and hence you get a long exact sequence of the K groups. Okay, so very good. So why do I apply? As I said, suppose X is a Noetherian scheme and Z is a subscheme, closed subscheme, and U is the open complement. Then you can write down, I mean, let's look at the middle line, Kn subscript Z of X to Kn of, sorry, Kn, I mean, KOH subscript Z X to Kn of COH of X to Kon of COHU. Of course, this Q star is given by the restriction of the sheaf, okay? So if you have a coherent sheaf, you just restrict it to U. And this category is the category of coherent sheaves whose support is in Z. Okay, so this will be a subcategory of COH of X. So you have a map. Okay, that's an exact functor easily, and that can be identified using the VCAS that I just said to the K-theory of coherent sheaves on Z reduced. A closed subset has many subscheme structures, so you can pick one, and I pick Z reduced induced closed subscheme structure. Okay, good. So I mean, and why does it work? I mean, I didn't write it here, but why does it work? I mean, I just said this follows from the previous theorem that localization theorem that I stated. See, COH of U is the quotient of these two categories. Okay, so it is quotient of COH of X over COH subscript Z of X. Okay, and so this is something we want, and you may have noticed that I do not state it for category of projective models. Okay, there is no such thing. There is no map from this iota star I wrote. I mean, given a projective model, I mean, coherent sheaf. I mean, how do, I mean, this is projective models, and how do you replace this? Okay, so you can talk about projective models over Z reduced, a closed subset, okay, A mod I, okay, but that will not be a map of projective models. I mean, this direct image is not going to be map of projective models. Okay, good. So anyway, I already commented that this is chapter 7 I'm moving on to. I already commented that K1 C of R is same as K1 R. By K1, I mean K1 of projective models, not coherent models. Okay, so this needed a proof. Okay, so I mean, I'm just saying that I simplified this proof. Okay, classically, what happened is they define something called plus construction. They define S inverse S construction. They define Quillen category, which I did. Okay, now S inverse S construction reconcile these two sides, and classically they knew that plus construction K-theory K-theory that you get using plus construction is coincides with classical three groups in classical K-theory. Okay, now nobody had time to check that you can give a direct proof. All the literature you see, they will say, okay, I mean, you just go to plus construction, and this involves homology theory. Okay, so and I entirely avoided homology theory. Okay, although homology theory will be the first course in algebraic K-theory, but somehow that's not what is needed. Okay, good. What else can I do? So K-theory of rings. Yeah, I mean, I'm trying to set up some notation. I use this COH of a category of finitely generated A module, and P of A is the category of finitely generated projective models. Okay. Then I will use the notation GN. K-theory of finitely generated modules or coherent modules is sometimes called G-theory. Okay, and we use the notation GN for the groups, and KN corresponds to K-theory of projective models. Okay, so main theorem here is that if you have a polynomial ring, okay, then K-theory of the ring and the polynomial ring agrees. Okay, I cannot say this for regular. For projective models. K-theory does not agree. Meaning, K-theory of A will not agree with K-theory of AT. But if you assume A is regular, then G-theory and K-theory agrees, as I said. So you can state this theorem. Okay. Now this is a question for maybe now. Okay, so can you use Lindel's theorem to prove this theorem? Okay, projective models are extended over a regular ring. Projective models are extended. Okay, but you have not proved that this is equivalence of category. Okay, so I am asking, I'm asking, this is commutative algebra question, whether there is a way to prove that. And so can you give a natural isomorphism from P to P bar tensor AT? Okay, and if you read the proof, if you become familiar with K-theory, you will probably be able to ask other questions. Basically, I'm saying, is there a natural transformation from P to P bar tensor AT in the Q category of AT? I mean, this will suffice. Okay, so first line I said that I'm asking whether there is a natural isomorphism. Of course, there is an isomorphism, I know, I mean, it goes through, I mean, reducing the thing to local case and then go to analytic isomorphism and improve it. Okay. Can you decipher it and prove it? And see, and more, you know, I mean, I'm saying Ravi, but of course there are younger projective modulists, okay? More, I mean, how about K1? Can you give a simple proof of K1? K1 of A is isomorphic to K1 of AT. Okay, so so I'm giving you a problem. Okay, I stated some, but if you read it, you may be able to formulate more questions. Yeah, any question?
Yeah, Satya, there is a question that the tensor is over what ring?
Huh?
The tensor product is over which ring here?
Of course A. Of course A. If P bar is P mod TP. Okay. So you have a projective module over AT. Okay. So, and we know that P is isomorphic to P bar tensor AT. Yeah, I'm sorry. I mean, I assume everybody knows projective modules. Okay. So we know that a projective module over a regular ring. Okay. You may assume, we may have to assume it contains field or such things. Okay. Those things you can assume. The projective module is isomorphic to P bar tensor AT. We know this. Okay. So we say projective modules are extended from the base ring. Okay. So, yeah, I mean, okay. Can I move on? Yeah. So, yeah, good. Now, you know, as I said, you know, I mean, you cannot do very much in affine case. So we have to talk about schemes, okay? So anyway, so, you know, I mean, I declare that scheme theory is part of commutative algebra. You know, scheme theory is easy, okay? I mean, everything you check locally, which is commutative algebra, okay? So, and as I said, you know, I mean, there is not enough open subsets in the category of affine spaces. Okay, you know, and as I said, I'm taking the view of I'm taking a pedagogic view, not necessarily a research view. Okay, viewpoint, and so you know, if you have, this is what I believe, if you have a theorem, whether you're a researcher or a student, if you have a theorem in affine case, meaning for commutative rings and modules, you should be able to write a theorem on quasi projective schemes. Not all schemes, but quasi-projective schemes, or at least projective schemes. I mean, you just have to translate you just have to write a analog of what you prove for graded rings, graded modules. That's more or less what it takes. Okay, if you are familiar with. Okay, so I'm giving you this. Okay, so in any case, so we'll be talking about schemes now on. Yeah, I mean, a lot of things now on wouldn't make too much sense unless, yeah, I mean, for in affine category. You know, in affine category, I cannot even have a long exact sequence. Okay. Anyway, once again, G theory, I mean, K-theory of coherence shifts is called G theory, and we use Gn of x to denote the group, okay? And K theory of the locally free shifts is called K theory, and we use Kn. And right hand side is the K theory space, and yeah, that's the loop space of the classic affine space. Okay. Okay. So you may, if you just I put on red the statements on groups. So if you want to focus on that, that's fine. So first and foremost, I have a map from inclusion functor from category of locally free shifts to category of coherence shifts. Okay, so this is an exact functor. So it's not a surprise that it will induce maps from K groups to G groups, and likewise K-theory space to G-theory space. And if X is regular and separated, then we have the same. Okay. Sorry. These are isomorphism. Regular and separated, these are isomorphisms. These maps are isomorphism. This I stated more or less corresponding theorem for projective models. Okay, basically everything has a resolution. Every coherent ship or like modules have a finite resolution, and that's why this works. Okay, so it will be the same proof more or less. Okay. Okay. So anyway, if just I mean, anything you do, okay, in this game, if you have a map, you want to define pullback and push forward. Okay, so in K-theory, we would like to do that. So if F is a map from X to Y, okay, so F star be the pullback map, pullback map. F going to F star F. Actually, this is locally defined by tensor product. So if you're thinking of module, I'm talking about tensor product functor. Okay, this is not necessarily exact, but in any case, if you restrict this functor to projective category of projective modules, it is exact. So you have map of the K-theory spaces. And on the other hand, if F is flat, then also this is an exact functor on the category, okay, on category of coherent shifts. So you have maps, okay, and so we would like to have a little bit better than just assuming flat. Yeah, I can more or less say most often nothing works for category of locally free shifts. Okay, everything works for category of coherent shifts. So for projective models, almost nothing works. Okay, and this theory doesn't work. Okay, but so only time you can make comments on. I mean, you have to assume regular. Okay, then they coincide, so you can make statements about category of locally free shifts. Okay, so I said nothing works, but with lot of work, something works. Okay, so anyway, so this technique is same. That's why I'm just going through this. So if you have so you assume that Y has enough locally free shifts, meaning everything is image of a locally free shift. Okay, let's not. I cannot take this for granted in this situation, and assume F has finite Tor dimension. So if you are thinking of modules, finite Tor dimension, you understand A to B, you have a map of rings. So B has finite Tor dimension if Tor F comma B vanishes beyond certain number. Okay, so I'm assuming that I define a subcategory COH F comma Y, that is all F in COH Y. Okay, so this makes perfect sense in affine case. Okay, so f in COHY, so that torr of f comma OY is 0 for all positive k. Okay, and because of this condition, if you restrict your original functor, okay, that's exact. Okay, so this is a trick used often, and then so you can define maps of K-theory spaces of this subcategory. Okay, K, COH, F, comma, Y. This order is important for me because I use, soon I will use the opposite order also for something different. Okay, good. But you still do not have a map from n of Y to Kn of X. I mean, I should say Gn of Y to Gn of X. But what happens is that this subcategory that you have, any object in the parent category COHY is resolution, has a finite resolution by objects here. Okay, objects in this subcategory. So by resolution theorem, these two are isomorphic, groups are isomorphic, and map of the K-theory spaces is an equivalence. Okay, so I mean, so I can combine these two maps. So, and I have a map from Gn of Y to Gn of X. Okay, so I define pullback, assuming that I mean X to Y has finite Tor dimension. Okay, so finite Tor dimension. One example will be if the upper one has finite projective dimension. Okay. Of course, flat. Okay, I don't think I have too many examples of such things. Okay, but anyway, now push forward. Okay, push forward. You see, I mean, suppose, so push forward is basically if you have a map from A to B of rings. Okay, then a module over finitely generated module over B is not a finitely generated module over A. So it is not a, it doesn't give you a functor from COHB to COHA. So those issues I have to resolve. Okay. So if F is a map of the projective morphisms, projective morphisms is what basically we'll be writing down theorems about projective morphisms. Okay, so then higher direct images have this property. If you have a coherent shape on X, higher direct images is a coherent shape. Okay, and I didn't define higher direct image. I will define. I'm too ambitious today. Okay, R0 F star F it will be just direct image. Okay, yeah, that means considering if you have A to B, you have module over B, you consider it as a module over A. That's all I'm doing. Okay, so what is projective morphism? Let's look at the second diagram first. Okay, so if you let's define projective morphism X2 spec of A. So it is just a closed immersion, okay, to the proj of A T0 T1 Tn, so projective space over A, okay, and followed by the projection. Basically, it is just a closed subscheme of Pn of A, okay, and that can be that is extended this way for a projective morphism from X to Y is like this. Okay, so so I want to define higher direct images. So what you do, you take a given a F in quasi-coherent is fine. Given a F quasi-coherent, you take an injective resolution. Okay, you did this for X10 to define X10 such things. Okay, so I'm going to the same thing. So you can take the global section, complex of global sections, or all of them have higher direct images. Okay, so I can take these two. Now I look at the homology of this. Okay, like X. Okay, homology of this HKX comma F is defined to be Schiff homology of the homology HK of that first sequence is the Schiff cohomology, and RK F star F, the higher direct image, is the homology of the second one. Second one is a Schiff, coherent Schiff actually. And what, like X, what you have map from, if I give you an exact sequence, K to F to G, like X, you have a connecting homomorphism and a long exact sequence. Okay, that's higher direct image. Okay, now so if I I did that. Given a map from X to Y, I defined higher direct image. Okay, this is a quasi-coherent Schiff. I mean, I assume F was a quasi-coherent Schiff. I also defined projective morphism, and this is a theorem that is useful for my purpose. That if F is a quasi-coherent Schiff, then all the higher direct images will also be a quasi-coherent Schiff. And it vanishes, they vanish when K is large enough. And you can twist it, okay, large enough so that all RK F star Fn is 0 for all K bigger than or equal to it. Okay, so this is useful. Now, I want to, let's take a projective morphism. I'm trying to define push forward for Kn, okay? So I am going to use the same thing, same method. So you look at K, define COH X comma F, all coherent shifts whose higher direct or positive for K positive RK F star F is 0. I defined a subcategory. Okay, like last time, and you can check quickly. I mean, this is a standard trick. Okay, that F star is an exact. When you restrict your original F star, direct image function, F star is a exact function. Exact function. So I have a map of the K-theory spaces. Okay, and then what happens is that you can, like last time, I will have given an F, I have a resolution by F opposite direction. I mean, we in projective models, we always have a resolution from left. Here it's from the right. Okay, so FK coming from the subcategory you define. Okay, I didn't tell you that, so this is you can think of this as a resolution in the opposite category. This is simple trick, but you can define this in the opposite direction. So you can think of it as a resolution in the opposite category. Okay, and if you want to, and actually opposite category, I didn't state this, opposite category is K-theory. Yeah, will agree with the original category. So basically I'm saying that this thing, that K-theory of COH X comma F coincides with K-theory of X by resolution theorem. So same trick I used. Okay, so I have a map. So I have pullback, push forward. Okay, so I push forward, I define for projective morphisms, and pullback I define for those which has finite projective dimension. Okay, finite Todd dimension. Okay, so now I have projection formula. If you have a projective morphism, I wrote with parenthetically proper, meaning so it works for proper, but I wouldn't go to the definition of proper. But anyway, you can, and all the applications are for projective morphism. So I'm assuming F has finite third dimension. Okay. I am also assuming X and Y support ample bundles. Okay. As I said, you cannot assume a module is image of a or coherent sheaf is image of a locally free sheaf. Okay. You cannot assume that. Okay, like category of coherent modules, meaning finitely generated modules. So I have to assume that. And in this case, anyway, I define action of K0 of X, at least in the affine case, I did that over Gn. Now I have this projection formula. I do not know how much you like this theory, but this is what they do. They write a lot of any Chan class, Chow groups and everything. Projection formulas are important things. Okay, they prove. Okay, so F star X times, so F star Y is F star X times Y. For all X in K0, K0 acts on Gn, so X times F star is the pullback, okay? So which I define, okay? And you then push it forward, and so that gives you the what you expect. So diagrammatically you have this, and so okay, I did that. Okay, and so I wrote a projection formula. Okay, for any projective morphism. Okay, so I think more often what more popular theorems are, you take any Noetherian scheme, you take a locally free sheaf on Y, say it has rank R, you look at the proj of the symmetric algebra, and most of you would know this definition of PE, okay? So, by the way, all this background on scheme theory I learned from Hurston chapter 2 and 3. Okay, so P of P, you look at the proj of symmetric algebra. By the way, and this works even for projective module. If Y is affine, I give you a projective module. Okay, you look at the symmetric algebra of the projective module and look at the proj. Okay, so and there is a map F of P to Y. Okay, and P has a this canonical line bundle. Okay, this O of minus C. So that represents an element in K0 of PE. Then what happens is that you actually Gn of Y, this lower one, if you think of this as spec of A, so Gn of A to the power R is the rank, is same as Gn of this P of E. Okay, so sending the map is the usual suspect using this, so zeta, you can talk about zeta to the power k by raising it, by taking product, okay. So that finishes this chapter 9. Actually, there is filtration by support and Gersten complex. Gersten's complex is a serious mathematics. Okay, actually, if you go to Gersten complex, this Gersten conjecture, you will be able to define Chow group that you have in Fulton as Chow groups as sheaf cohomology of Kn. Okay, that's an important theorem. Okay, and anyway, I'm skipping that. Okay, there are more projection formula. So last one I stated for I have 5 minutes. Stated for coherent shifts. This one I'm stating for locally free shifts. Okay, so you, as usual, you take locally free shift of rank R, PE is the same, zeta is the same. Okay, then Kn x to the power R is isomorphic to the K-theory. Same theorem works. Okay, same theorem works. Okay, and this proof is a little more harder. Basically, it is the same proof, you can say. Okay, but there is a you walk a tightrope. Proof involves is involved, and there is something called this. You may like to know. Some of you may like to know. You know that there is something called canonical resolution of regular locally free shifts. Regular locally free shifts. I'm not talking about regular. There's some locally free shift defined to be regular, and they have a resolution. Okay, and then I mean, not difficult, but one needs to. I seriously mean it's not difficult. Okay, and so very good. Last chapter, K-theory of quadrics. You know, Swan gave a. I think this is the best application of K-theory. Okay, Swan in his paper in Annals, okay, he gave a version of this prediction formula for quadrics. Okay, so you take a degree 2 homogeneous polynomial. Let's say this is smooth and such things. Okay, then he has a version. Okay, and why is interesting and important is that because you want to know the K-theory of spheres, affine sphere. Okay, and you know affine sphere is same as the open subset in this proj. In this proj, you write summation xi square minus t square. In this, you substitute t equal to 1 or t not equal to 0. That's your sphere, and you can write down. So if you have an open subspace, you have the closed subset. You can write down the long exact sequence. Okay. Let me quickly go through this. So you know, given a quadratic form, you have a symmetric bilinear form, and Qx is 1/2 of Bxx. Okay, and so a quadratic R module is a pair. So I'm just trying to generalize the idea of quadratic forms. Okay, we like to generalize. Okay, whatever. So where P is a projective R module, and phi is a map, symmetric map, P to P star. Okay. So, I mean, this is symmetric. Okay, we can define Qx to be 1/2 Px x. Okay, so you can see I'm assuming 1/2 is there in the ring. So such a thing is called a quadratic R module. Okay, and then what happens is, I saw it only in Swan's paper. Okay, so you look at modules of all quadratic forms. Okay, and symmetric algebra of degree 2 elements in symmetric algebra in P star of P star, you know, these two are isomorphic. These two are isomorphic. This you can give as an exercise to your students. Okay, this is an isomorphism. Okay, so I said P comma Q. If P comma Q is a quadratic R module, its pre-image I'm denoting by Q itself. So you have a ring, homogeneous ring. Okay, you have a homogeneous ring, and so you mod out by the ideal generated by Q, and correspondingly you have Proj of SQ. Okay, and I say P comma Q is non-degenerate if that map phi is isomorphism, and that helps. Okay, that helps in the sense then the corresponding map from XQ, which is proj of that ring to spec of R, is smooth. Okay, as I said, we like to generalize, but what I'm interested in the sphere. So you look at, I am looking at QD, okay, which is summation xi square, 0 to d, and QSD with sphere QD equal to 1 in mind, I define QSD summation xi square minus t square. Okay, but anyway, I will state that general theorem. Okay, so so these are some facts. But anyway, basically, there's not much facts here. You know, basically, you have AQ is the symmetric algebra. This is the affine scheme. This is the symmetric algebra over. So yeah, I mean, so XQ is the XQ is t equal to 0. Okay, and U is t not equal to, you know, when t is not equal to 0, this becomes an affine space. So AQ is this. Okay, so in any case, I mean, looking at this sub-scheme, okay, looking at this closed sub-scheme and this open sub-scheme, I have a long exact sequence. Okay, now I'm look at this iota star I did. This is the map between the closed subscheme induced by the map of the closed subscheme. Look at this. Okay, and Swan's theorem. This is my I star. Swan's theorem says that. Yeah, I mean, this is what is the projection formula that I did not state. Swan, I mean, is really incredibly smart person to, you know, this thing that I told you, this resolution that would be generally infinite resolutions. He somehow cuts it down. Okay, I'm using this Clifford algebra. I am already 3 minutes above. Let me quickly say. So Clifford algebra PQ. So of course I am not defining Clifford algebra. These are finite vector spaces. Okay. Okay. In particular, so basically, you know, by replacing these two, somehow I will write down let me so I mean, let me tell you that punchline here is that K0, the algebraic K0 of the sphere of the corresponding ring is same as topological K0. Okay, this is Swan's theorem. Okay, this is this I am very. I mean, when you can relate two areas of mathematics, I feel very good, and this is one serious example of that. And so if R is regular, we have basically, of course, I'm rushing, and this is probably the last slide. So you know, I wrote down a long exact sequence here, where everything is ring. There's no thing here. There's no thing here. Okay? And I mean, these maps are all natural. Okay, I mean, so you know, this is the so you have computed K-theory of sphere. Okay. Okay, thank you.
Thank you very much, Satya, for your interesting talk, relating so many things. And I hope we will see the book very soon. Are there any questions? So the audience can unmute and ask questions. Ravirao, you have a question?
Yeah, Satya, you asked me one question in this talk. Okay, so can I ask you another question in return?
Okay, here.
So my point is, Swan has done it for the sphere, but one should really do it for the algebraic sphere. And
What do you,
the
what do
algebraic sphere sigma xi yi equal to 1.
that's what he did.
No, he did for sigma xi square equal to 1.
And what are you saying?
Sigma xi yi equal to 1.
Sigma xi yi equal to 1. Yeah, I mean, this
It
this is
doesn't come automatically.
by the way, this is probably covered in that. I am not 100%
No,
sure.
it is not covered. It is not covered. It was begun by Suslin in his paper on on cohomology of K-theory. He did
Okay.
it. He started it. But there is much more to be done. And that's
Okay.
quite hard and quite interesting to do it.
Yeah, it will be good to explore. And I mean,
Yeah.
so you are essentially endorsing my point that there are things that we can do. I mean,
No,
commutative.
lots of things to be done, but your question of Basculin is very tough. People like Mumford and all, they have tried to do it in some ways, get other type of proofs rather than the Lindell proof. Mumford actually had Lindell's proof to some extent, but nobody else really thinks in
No,
a different way. Artin, for example, Artin also has a way of thinking which involves going to completions and so forth. But none of them are really going to give a completely categorical argument. It's not possible easily. That's what it looks like.
I am not expecting anything easy. If things are easy, then it's not a good paper. Okay.
No, this is a difficult paper. It
Okay.
is not good. It is a
But,
difficult paper.
but, but what I would emphasize is that commutative algebraists did not put enough effort into this. Just didn't do it. You are talking about Mumford and such people. Okay, I mean, no. I mean, we didn't give our mind to this, and there is a lot of scope. Okay, I mean, just don't do. Yeah, I mean, I give you very. I think this is I mean, I don't know why I said I gave you. I would like to solve this problem. Okay, but okay, I also evolved, and I don't know how much more I want to do. Okay, so but I'm saying, I mean, just you just write. I mean, study K1 of the category of finitely generated module. Okay. And yeah, why not K1 of the problem I said? Don't do. If you cannot prove the whole thing, just prove K1 exists. Just give an elementary proof. As I said last time that how many proofs of stress conjecture we have. Okay, and why not these things? I would really love to see proof that K1 of A is isomorphic to K1 of a T or a regular irrational between us about A. Okay?
Yeah. Any other questions or comments?
And my book, I mean, yeah, I am pessimistic that some reputable publisher will publish it. I'm trying to work with them, but um, I'm not assuming that will happen. But one place they cannot stop me from publishing it. That is archive. So if nobody publishes, it will come here. Okay. So I mean, I mean, by next year, this time, if nobody publishes, it will probably be on archive.
Okay.
And then, okay, good.
Yeah. All right. So I don't see any further questions.
Okay, thank you,
I
everybody.
had a very elementary naive questions. We see many times theorems about real field, projective modules over real surfaces. And so can we replace R by real closed field? in those theorems?
Because I did not look it up. Okay, I mean, I told you I'll look it up, but I did not. But there is some result. I forgot whether it is for finite fields or for certain fields. I will have to look it up, and I will write you an email. Okay, and that's something I didn't include in my book. Referee commented, there's not much application. I mean, I think Swan's application is the best application. And there is something about finite, some fields. I mean, I forgot whether it's for finite or not. Okay. So I will look that up. Okay.
Okay. Thank you. Thank you very much, Satya, once again for a very interesting talk and talking to all of us. And I hope
Yes.
many young